Hi, Trenton. So let's talk about this problem that was giving you trouble. Uh, Before we talk about it, though, let me just say that these problems aren't easy. So you certainly shouldn't feel bad for not being able to solve them. And I also understand your frustration with these problems. Again, they're not easy problems. So if you have trouble with them, it's not a big deal. Okay, so let's first just get a global idea of what we're doing. So if somebody asks you to calculate the probability of anything, this is what they're asking you to do. So they're asking you to compute a fraction where in the bottom of the fraction is just the total number of things floating around, the size of the sample space, whatever you want to say. And the top of the fraction is the number of those things that you're interested in. So this is always true. And of course, what makes these problems difficult is that this fraction comes in two pieces, and one or both of those pieces might be difficult to find. So in the particular problem you're interested in, you're always taking a samples of size 4. You're always looking at 4 engines. So the bottom of the fraction is the total number of samples of size 4. And the top of the fraction is the number of things you're interested in. And so since you care about the probability of the container shipping, that means that since it shipped, that there were no defective engines in the sample. So you want to know how many samples of size 4 are there where you don't have a defective engine. So this fraction is what we'll compute for this problem. Okay, so here is the problem. So there are 15 engines total, and the company chooses a sample of size 4, and if any of the engines are defective, they won't ship. So find the probability that the container does ship, even though there are 2 defective engines in there. Okay, so let's think about this. First of all, it's nice just to have a visual, so let's just picture the container as having 15 engines, and let's just call them engine 1, engine 2, etc., up to engine 15. And there are 2 defective engines in there, so let's just say that 1 and 2 are the defective engines, just for simplicity. The logic of the problem doesn't care which 2 of these numbers represent the defective ones, so you could say let 5 and 13 be the 2 defective engines, but whatever, just give the defective engines whichever 2 numbers you care about. So for me, that's 1 and 2. Okay, so let's start by thinking about the bottom of the fraction that we're going to compute. How many samples of size 4 are there? What's the total number of samples of size 4? Well, to answer that question, I guess let's just get a handle on this. So here are a few of them, right? Here's a sample of size 4. Maybe they get engines 1, 4, 7, and 9, or 7, 8, 9, and 11, etc., right? So if you imagine listing all the different possibilities out here, you can see that there are quite a few of them. So we're expecting a number bigger than like 10, right? We're expecting a big number. So to make the language more formal, to make it match up with what your textbook does, you want to know how many combinations of 4 engines you can get from 15 engines. Okay, so how many ways can I choose 4 engines from a total of 15 engines? Well, the answer is 15 choose 4. And I think this is the notation your book uses. So 15 choose 4. So I'm choosing 4 from 15. And so here's the formula for that. I just plugged in the 2 numbers. So you take the total number you care about factorial divided by the number you're interested in 4 factorial times the difference of the 2 factorial. And what comes out the other end is 1365. So there are 1365 total ways that this company can sample this container. There are 1365 ways that you can get 4 engines from a total of 15 engines. So that's going to be in the denominator of our fraction when we compute the probability. That's the total number of things that we care about. Okay, so this part is trickier. Of those 365 total combinations, how many of those contain a defective engine? Although I guess in this case we care about how many contain a non-defective engine, right? Because we want the container to ship. But actually answering this question I think is easier. And so let's focus on this question for a second. So let's just think about how many ways we can get a defective engine. Because if you can figure out how many ways you can get a defective engine, then you can also find out how many ways you can get a non-defective engine. Right? If you answer one question, you've answered the other. So let's just focus on this question. And let's make this simpler for a second. We've already assumed that engines 1 and 2 are the defective engines. So let's just focus on a piece of this question. So how many of these 1,365 combinations contain the first defective engine, contain engine 1? So here's our visual again. And if we're thinking about samples of size 4 that contain engine 1, essentially we're saying, okay, engine 1 is already off the table. So we have a sample of size 4 and engine 1 is already in there. Okay, well what's left? Well, engines 2 through 15 are left. And if we want a total sample of size 4, then now we're talking about choosing 3 of these remaining ones left. Okay, so engine 1 is already inside our sample. So engine 1 accounts for one of those engines. And so now we need 3 more engines that will come from this list. Okay, well, now we're talking about choosing 3 engines from a list of 14 of them. And so there are 364 ways to do that. 14 choose 3 is 364. So if you've already removed engine 1 and put it inside your sample, there are 364 ways of filling in the rest of the sample, of choosing 3 more engines from the remaining 14. Okay. So on the next slide, I'm just going to ask the same question, but for engine 2. How many of these combinations contain engine 2? Well, the logic is exactly the same. So if I come back here, and if instead of removing engine 1, I leave 1 where it is, and I remove engine 2, you still have a sample now with engine 2 inside of it, and you want to fill in the rest of the sample with 3 more from a remaining list of 14. So removing engine 2 gives you the same result. So there are 364 samples which contain that defective engine also. Okay, and so from your email, I'm not sure, I think you had trouble starting, right, which is perfectly fine. So you might not have gotten to this point. But let me show you what usually happens at this point. There's a subtle error that many students make that's perfectly natural. So here's the idea. Okay, so there are 364 samples which contain engine 1. There are 364 samples which contain engine 2. Okay, so it's natural enough to add those two numbers together, which says there's 728 samples which contain engine 1 or 2. Okay, well what would that mean? If we take that number away from 1365, that means there's 637 samples which don't contain a defective engine. So there's 637 samples which are okay, which would result in the container shipping. Okay, well if that's the case, if there are 637 samples that don't contain a defective engine, then that's the numerator of our fraction. So the probability that your sample doesn't contain a defective engine, and therefore the probability that your container ships, is 637 divided by 1365 equals 47%. So 0.47. Okay, so at this point, if you're curious, you might want to pause this and see where you can find the error in this thinking. But in any case, let's think about this logic. So let's look at a sample like these. So here's a sample of size 4. It contains engines 1, 2, 3, and 5. Here's another sample of size 4. It contains engines 1, 2, 7, and 9. Okay. These samples contain both engine 1 and engine 2. Okay, so both of these samples show up in this 364 right here, the 364 samples that contain engine 1, and they show up in this 364, the 364 that contains engine 2. Okay, well that's bad. That means that you've counted each of these samples twice. You have double counted, which means that your numbers are inflated. Okay, so if you just add these two numbers together, you're taking some samples and counting them twice. That's bad. So the kinds of things that you're counting twice are the samples that contain both engines. So let's just figure out how many of those there are and subtract them off so that we're not double counting anymore. Okay, so how many samples contain engine 1 and engine 2? Okay, so let's think about this. You have a sample of size 4 and you're assuming that 1 and 2 are already in there, right? That means there are 13 remaining engines from which to choose, and you need 2 of them. Okay, so there are 13 choose 2 ways of getting the remaining 2 engines, from getting 2 engines from the remaining 13, and 13 choose 2 is 78. Okay, so there's 78 ways that you can get both engines 1 and 2. Okay, therefore the number of samples that contain engine 1 or 2 is this, 364 plus 364, but now let's subtract off the stuff we double counted to make our counting accurate, equals 650 now, not 728 as we had up here, okay, where we didn't take this double counting into account. Okay, so there's 650 samples that contain either engine 1 or engine 2. Therefore, the number of samples that don't contain engine 1 or engine 2 is whatever's left over. Right? 1365 minus 650, which is 715. Okay? So there are 715 samples of size 4 that do not contain a defective engine. Okay, and the probability, therefore, that the container ships is 715 divided by 1365, which is about 50%, so 52.4%. Okay, so we have an answer here, but let me just again re-emphasize what we did. So here's the global idea again, right? We counted the number of things we were interested in. Now that counting was not easy, right? Calculating the number of samples of size 4 that don't have a defective engine was not easy, right? But we did it. And then we divided by the total number of things in the universe that we cared about, right? We divided by the total number of samples of size 4. Okay, so hopefully you can take this idea and adapt it to the other problems in this homework. But of course, if you have trouble, just let me know and send me another email.